Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Andy Tzanidakis with us today. Hello, Andy.
Hello, thanks for having me.
Well, thanks for agreeing to talk about your very awesome article, which we will get to here in a little bit. Let's see. Andy, what is your geolocation? Where are you at?
I am currently located at the University of Washington in Seattle.
Ooh, all right. Well, we are past equinox here, so I imagine that
Um,
fall is kind of coming into being there in Seattle.
yes, it is. We are very quickly going into fall mode here.
Okay, very good.
Yeah.
And I'm in Phoenix, and we ended up with well, we had the remnants of a hurricane come on up through
Oh,
through the Mexico and California, and that sort of blew away whatever summer was left, and we are
mm,
definitely into our fall mode now. So it's very nice. Temperatures are great. The humidity's down. It's
it's
beautiful.
amazing. Yeah, we just had a little bit of rain here today, but actually some sun is just shining in right now, so
Very
you
cool.
must be the good luck.
You must be. I bring sunshine. Very cool. Let's see. And Andy, what do you like to do for research there in Seattle?
Yeah, so I am really fascinated on really rare stellar eclipses. So
Cool.
I love discovering anomalous stars and big time domain surveys. And
Okay.
specifically, I'm really invested in the circumstellar environments near low mass stars.
Okay.
So thinking about things that are not planets, they're not stars, but they could be dusty things like
Hmm.
rings or, for
Blobs.
example, dust clouds.
Yeah.
And these are really fascinating. They're really peculiar, and they've fascinated me for a few years now. So that's been a big focus of my dissertation work here at the University of
Very
Washington.
cool. Is this your dissertation work on this one?
Yes, this is part of my dissertation work as
So
well.
when did you
Yes.
when did you graduate?
I'm graduating in May of
Ah, you're
2026.
graduating.
So,
Well,
yes.
let me be the first to say congratulations, Dr. Tzanidakis.
Yeah, soon to be, hopefully,
Very
in the
cool.
next few
Awesome.
months.
Very good.
Yes.
And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can grab a copy for free, go get one. It's an awesome thesis paper, too. A systematic search for main sequence Dipper stars using the Zwicky transient facility. And Andy, take us away.
Yes, so this has been a paper that has been in the makings for almost 2 years now, and we're very stoked that we got to finally publish it. I just want to give a moment to shout out some of my co-authors, Jim Davenport, Nevin Kaplar, and Eric Bellum, who are some of my advisors here at the University of Washington. And
Cool.
then the last seven co-authors are from collaborators from the Dirac Institute,
Oh, yeah.
and specifically from the Link frameworks team, which is basically an organization at Carnegie Mellon and here at the University of Washington that
Cool.
basically are making tools to help us analyze complex time domains data
Nice.
on the scales of LSST. So they are the geniuses behind these amazing tools that we've done, that have developed to sort
Very
of
cool.
do this search. So yeah, I
Right.
just want to give them a
Otherwise,
shout out.
it'd be a lot harder. That was a great,
Yes,
great shout out.
yes.
All right.
Yeah.
Let's go ahead and get into it.
So you might be wondering, reading that title, what exactly is a main sequence Dipper star?
Yes. What is one?
And so the story kind of starts back in the early 2016s. You might have heard of a star called KIC 8462852, also known as Boyajian star.
Yes.
So this was a star discovered by Tabitha Boyajian using the Kepler Space Telescope.
Mm-hmm.
And what's often referred to as the Boyajian star is this what seemed to be an ordinary main sequence star had these really bizarre properties in its light curve.
Yes.
And it was particularly these optical dips that Kepler saw during its primary mission.
Cool.
And so we've dubbed this as sort of like the main sequence dipper analog to a lot of the work where this search has been inspired by.
Cool.
Um, what's really interesting about the Boyajian star is that there's a lot of gaps in our sort of understanding of what exactly caused this, and it's really puzzled the community for a really long time, and it still does. And there's been a lot of theories about what could be causing those optical dips that we saw from the Boyajian
Hmm.
star. So
Hmm.
there's some theories that talk about a series of exocomets, for example. There are some theories that talk about disruption of small bodies that could be producing these sort of dust-like eclipses. But the problem is that a lot of the properties that we see for the star are quite puzzling. So, for example, we
Yes.
don't see infrared excess, or a lot of the scenarios that the modeling work has done hasn't been able to fully explain the properties of the Boyajian star. So, in many ways, it's become this sort of mystery still of like, okay, well, there's all these theories about the Boyajian star, but we still don't really know what's going on. And there's an awesome paper by Jason Wright, who kind of lays out all these scenarios of what possibly the Boyajian star could be.
Cool. Very good.
So that was the Boyajian star, and of course, in many ways, there's been many other stars that I think that haven't been getting as much of attention and love in the community. There was this recent paper by well, it was several authors with the discovery of Assassin 21QJ,
Hmm.
which we believe to be a planetary collision between two bodies.
Cool.
And this one is kind of different because it has the sort of infrared excess that we typically see in the light curve that's being produced by these violent collisions.
Okay.
And this is not what we saw for the Boyajian star. So there's a little bit of a contrast here, even though some theories have suggested in the past that the Boyajian star could have possibly been a collision between two planets that are potentially like really far away. So
Okay.
maybe the dust isn't re-radiating in
Mm.
the infrared as
Ah,
efficiently. Um,
ah.
and then if you scroll down a little bit more in the discussion, the motivation behind this discussion is really to give a little bit of a broader context to the idea that there's all these systems that what they appear to be as main sequence stars, whether they're slightly younger or a little bit older, but they all appear to have these sort of like stochastic dimming events that are really complex and that we don't fully understand.
Cool. I'm with you.
Um, so another example is the famous J1407 system.
Hmm.
Has a really long WASP number. And this one we believe to be a disk eclipse that's coming from this system that with these like really large rings. So
Hmm.
perhaps analogs to a much larger version of Saturn, for example, with these large rings
Okay.
and can produce these really
Okay.
complex dips.
Yes.
Um, and of course, there's been other systems that have been discovered that kind of have these, again, one-off eclipses that are on these ultra-long period binary stars that have disks around them. And again, we usually get like one or two shots of like seeing these transits happen in
Yeah.
like, time scales that are maybe sometimes beyond the human life expectancy, which
Yeah.
is kind of amazing to think about that we really get one shot at this. And then, of course, the word dipper, we also hear it more commonly in the young stellar object community. So for really young stars, where they're still undergoing accretion from their disks, and
Right.
that can cause a lot of variability too. So we kind of raise it out to the community also to make those distinguishments of that you can get all series of this sort of stellar variability.
Yes.
So in this long discussion introduction of talking about all these systems that are perhaps connected to what we're pointing to is that perhaps here is that there's a continuum of events that we're seeing. So you
Excellent.
can have all these main sequence stars. Some of that might be disks. Some could be young, really young stars that we've not classified properly.
Hmm.
Um, and we're trying to really tie in the story with like that you can have a spectrum of events that are happening at the same time.
Nice.
So where this paper comes into play is that until now, really, um, there hadn't been a sort of rigorous search in looking for these analog systems
Right.
to the Boyajian star, to some of these systems. And so we used basically this opportunity using the Zwicky Transient facility to essentially go after and search for these stars.
Nice.
But we do this in a very particular way that we wanted to limit our sample in a specific part of the color magnitude diagram space.
Okay.
So instead of looking across all the stars that we could see, let's say with any given telescope, we
Right.
restricted our sample to looking at F, G, and K main sequence stars.
Okay.
And so that's where we start our analysis. We can hop on, maybe we could scroll down to figure one.
One, and we have a CMD. There we go.
Yes, a beautiful Gaia color magnitude
It
diagram.
is beautiful.
And so the background gray color map that you see here is the
Yes.
sort of yep, that all of that is basically Gaia. And then that orange slab that you see there is essentially our selection function
Okay.
of F, G, and K main sequence stars.
Yes.
And so we basically use a Gaia catalog to essentially make these cuts to select stars along this part of the color magnitude diagram space. So it kind of looks like a little banana. I call it always like the banana plot because it looks like we're like selecting like a very specific region there. And that's what we're trying to do, right? We're trying to restrict our sample to understand the photometric properties of these stars in that very confined color magnitude space.
Great. Perfect.
So
Mm-hmm.
yeah, so we do our selection using Gaia, and then we cross match that using the Zwicky Transient Facility,
Okay.
which is a ground-based time domain survey located at Palomar Observatory. And ZTF is amazing because it has been staring at the night sky for several years now.
Yes.
And so there's an abundance of photometry and light curves for many of these stars. Are both in the northern the ZTF is in the northern hemisphere, and so it could see a lot of the stars that we could also find with Gaia.
Cool.
And so we essentially cross-match these two samples,
Right.
and we begin to understand what that actual number is.
Okay.
And so in that final cross-match, we get about 62 million sources.
Okay.
So 62 million FGNK main sequence stars,
Okay.
which is a nice big number to look through. That's a lot of data.
Yeah, you're gonna need some tools for that.
Yes, yeah, absolutely. So before we talk about the tools, I then talk a little bit about how exactly do we go about in looking for dips in these light curves. So we have our 63, 62 million FGNK stars. We have all these light curves. But now the question is like, how do we look for stochastic dimming events?
Yes.
So we do a series of tricks and tests to basically find these dips.
Okay.
So what we do is you see in equation one, we essentially have this simple metric that's essentially calculating the deviation of a given ZTF light curve, either in the G band or in the R band.
Okay.
And we're basically measuring how much does a dip deviate from its by weight location, which is essentially like a weighted median.
Yes. Right.
And this is a little bit more robust against outliers because we don't really want to be biased towards things that are like, maybe like 1 point that just might have been, some genuine outlier instead of being like a real dip.
Okay. I'm with you.
So we do that, we compute these sort of running deviations of these light curves so we could basically find dips in the light curves.
Okay.
And once our code has identified these dips, we are essentially now trying to characterize these dips.
Okay.
Now, what this paper does a little bit differently is that in equation two, we essentially construct this new sort of light curve dipper score metric.
There we go. Cool.
Yeah. So this method is taking into account that ZTF is a ground-based survey, right? And so there's gaps, it's noisy data, right? It's not perfect. It's not like Kepler. And so we need some more robust scoring metrics that will reflect the quality of data that we have at hand. So essentially what this score takes into account is basically N is the number of dips. So like, let's say maybe a star has like 1 dip or it has like 3 dips, right?
Okay.
And so we penalize our light curves by the number of dips, and we take the logarithm of that, the ln of that. And so basically, we really want this scoring metric to find systems that have one-off dips, right? Because that will give us, the highest amount of score.
Yes.
And then we basically sum up all the dips that we find, and we multiply their properties, like for example, their amplitude. So that's that delta I, which is that, the
Equation.
deviation.
Yep.
Yep.
Equation.
The phi is basically the full width half max of the dip,
Okay.
right?
Yep.
And that is basically the number of detections, right? So
Okay.
for example, if you have a dip, but you only have one photometric point, is that actually a good dip, right? Maybe not. But
Uh,
if you had like, let's say something that had like a few detections, well, then that makes it a much more compelling case.
okay.
And then we penalize it by the chi-square of a Gaussian fit. So basically,
Okay.
if it's something that's clearly like an outlier, then this basically helps us normalize this a little bit
Great.
towards things that are kind of funky looking.
Very nice. Okay. I'm with you on equation two. We're good.
Excellent. Okay, great. So we essentially measure the score for all stars. We do it for the 63 million stars in the sample.
Okay.
So if you go to figure 4,
Sure. Let's
you will see,
your four histogram.
mhm, you can essentially see the log score distribution of,
Okay.
of all of our stars.
Stars, logs.
And
Yes.
so we've essentially broken it down to stars that have one, two, or three dips. And
Okay.
then the orange is basically all of them combined.
Yes.
And one thing that you'll notice, right, is that this seems to be fairly normally distributed, right?
Yes.
There doesn't
Yes.
seem to be, any clear bimodality in the sense like, whoa, like all the systems that have really high scores are on one side.
Right.
And so this was kind of a surprise, right? You would imagine though that like if there were things that had really high amplitudes, that they would be to the far right, they would have the highest amount of score.
Right.
And the other curious thing about this is that you'll notice that the number of stars in this is really, really high, right? We're like in the tens of thousands of stars that we're measuring this.
Yes.
So you could clearly see that's a lot of stars to consider that, potentially they have these dips that we might need to investigate, that they might be the next Boyajian star, for example, right?
And to get to a point you made earlier, right? There's no gaps in these distributions either.
Exactly.
Thank you.
So one curious thing was, well, why is this so smooth?
Yeah.
And it turns out that this is actually systematics. So actually, the figure that's right next to it, figure 2, which is going a little bit back,
Yeah.
is addressing a little bit about that issue.
Okay.
And we wanted to do our due diligence because we think it was so important to report the discovery of actually genuine bona fide systems. We really want to consider the effects of systematics.
Yes.
So here I'm just showing 2 examples
All
of
right.
these common systematics. So for example, the bottom row, you could see where the star is actually going in between the CCD edge of the ZTF detector.
Okay.
And because ZTF comes back to the same field, right? But
Right.
the position of that star might not be exactly on the same pixels.
Yes.
It'll jump around really close to the CCD edge.
Right.
And
Okay.
unfortunately, there's no way of really removing those systematics on the data information that's given to us by these data products. And
Okay.
and so in the paper, I think we make a very compelling call that, if we want to do these large searches, perhaps it would be beneficial for the community to also have, pixel level information about the photometry that we get from these surveys, because it could really help us address some of these systematics.
Good. Nice. Okay.
So it turns out that the systematics were actually really aggressive. It was like something like
All right.
80% to 90%.
Okay.
Now, of course, this was expected because like our algorithm was like looking after kind of systematics in a way, right? So it was clearly trying to select it. Not to say that the ZTF data isn't amazing, of course, right? But I think that it's just really trying to be careful with the interpretation right off the bat.
Good.
Yeah. I think careful work here is really important in that sense.
Essential, not wild.
So essentially, we cut down all of these candidates. We try to identify clever metrics of trying to remove pretty much all of the systematics as much as we can.
Okay.
And so we essentially get a pretty large list, about like, I think it was like between 20,000 to 50,000 stars that we had to manually kind of scan and
Okay.
optically and visually sort of scan.
Okay.
And so this essentially means like looking at the cutouts and making sure that there isn't really anything weird about the images.
Mm-hmm. Mm-hmm.
So we do that. And one more figure that I wanted to highlight was actually figure 5.
Okay.
So on top of addressing the systematics, the other thing that we wanted to understand is the pipeline efficiency of our Dipper metric finding
Okay.
algorithm.
All right.
So here you're looking at essentially the time scale of an artificial dip
Okay.
with respect, so on the x-axis, and then on the y-axis, you basically have the transit depth, right? So it's 1 minus the normalized flux.
Uh,
And
yes.
and then we've shaded it basically by the detection efficiency. So what we do is we take a bunch of flat ZTF light curves with
Mm-hmm.
no dips, and we artificially inject, some
Mm-hmm.
parametric form of a dip. We
Yes.
we we kind of vary the shapes and the durations and the amplitudes, and then we basically pass it through our pipeline, right? Like we evaluate the score, we kind of pass it through different sort of times of observation, through different cadences and different depths.
Cool.
And essentially, we come up with a sensitivity map, which is essentially telling us that our ZTF and our detection sort of framework is about like 100% sensitive to things that are above around 30% or so of dips.
Yeah.
So right around exactly where we would typically expect for ZTS photometric precision to give us. And of course, it makes sense that things that have like really small dips, then we're gonna struggle a little bit more. So the
Sure.
detection efficiency kind of drops off there quite dramatically.
Great. Great.
Yeah, so somewhere
Well,
around there. Yeah.
we're pretty good on some
So
skills of, 1 to hundreds of days. Um,
yeah, yeah, and there's definitely this was only using single dips, and so perhaps in other versions of these kind of analyses, perhaps it makes sense to also do multiple dips, and to try to induce even more realistic sort of physical constraints on the light curves themselves.
a little bit of structure at low time
Yeah,
scales, right? You sort of
yeah,
wave out. Uh-huh. Okay.
yeah, for sure.
Cool.
So we're fairly convinced that we could detect these systems with high efficiency.
Yep.
And so that takes us to section 4. So we discover
Pretty
81 new systems, and
nice.
it's a very particular number. And of course, this is because we had to like vet through a lot of these, and there might have been some that like it was kind of hard to tell. So we had to really manually vet through all of these and
Well, we
make
went
sure
from
that they were
62 million to got 81 good candidates.
yes,
Yeah.
yes, yes. So
Okay.
these are 81 new candidates. And
Cool.
so, we go back to essentially the ZTF data products through URSA, and we look through the pixels. We're taking basically the most confident photometry that we have.
Nice. Okay.
And so we believe these are 81 new systems that we deemed as important. So in this section, we talk about the properties of these systems, which takes us to figure 6.
Let's go to figure
Now,
6. Property
figure,
and
yeah, so figure 6 to me tells a lot of the story of these really interesting systems. So in
indeed.
black
Okay.
are the 81 newly discovered systems.
Mm-hmm.
And again, we're looking at timescale versus transit depth, right?
Yes.
And I've color coded in different scatter plots, basically other analog systems. So we have the Boyajian star, which is in the pink star.
Hmm.
We have some other systems which are like disk eclipses. And so you could see that ZTF is actually filling in a very specific phase space in the duration and amplitude of these dips, which has never been explored before.
Very cool.
Yeah, so we were actually quite surprised that we found so many that were sitting around, the 100-day time scale
Mhm.
of these events. One other thing that sort of emerges from this is that you might notice that the ones that are really close up to 1, right, those are the highest amplitude ones. Those seem to be more rare, and that was actually quite a surprising finding that we're quite puzzled by. You would imagine, right, that we're most sensitive to the high amplitude stuff
Yeah, from that sensitivity. Uh-huh.
from that sensitivity, right? And so
Right.
we only found three systems that have, really high amplitude dips,
Okay.
which is quite interesting. So,
Cool.
perhaps there's something there to that, but it seems like it's more common to have dips that are low amplitude, and the average time scales are about like 100 days or so.
Right.
And
Okay.
so there seems to be a
Okay.
lot of overlap here in these in this phase space.
Mm-hmm. Mm-hmm. Interesting.
So yeah. So if you go down to figure, let's see. Actually, yeah, let's go down to figure 7.
Okay, let's slide on down to
hmm You can actually see an example of what some of
oh,
these light
cool.
curves look like.
Okay, good.
Truly,
Good, good.
truly bizarre. These are not your typical light curves that you get to see in main sequence stars, right? You have things that are essentially disappearing for
Yeah.
a couple of weeks to months, things that have very bizarre transit shapes that so this is giving you a little bit of the idea of the diversity of
Yeah,
light
the,
curves
the
that we're seeing.
flavors. Very
Yeah. So in table 1, we've basically visually inspected these light curves, and we've kind of broken them down into essentially what we think as symmetric, so things that seem somewhat symmetric in their dips, things that are asymmetric. So
okay.
for example,
Find table one.
yeah,
There we go.
it was right
Ah,
on
here we
top.
go.
Yeah.
Symmetric, asymmetric,
Yeah.
erratic. Okay.
So yeah,
Okay.
so about 43% of our sample actually contains asymmetric depth. So
Oh,
either the ingress is really long or the egress is really long,
gotcha.
one or the other. And then there's stuff which is erratic, which is like basically there's no structure to it. It's just kind of like it's going up and down and then it stops. So it
Mm.
seems like it's more of like a state change of whatever we're
Ooh,
seeing.
ooh, interesting idea.
Um,
Okay, right.
yeah. So this kind of gives you sort of an idea of the different light curves that we're dealing with.
Mm-hmm. Yeah, the
Um,
cross-section are sort of symmetric, so yeah,
yeah, there's some symmetric ones in there as
there
well,
it
for
is.
sure. And yeah, there's one really cool light curve. One of my favorite light curves from this paper is figure, I believe, 8.
Eight.
So yeah, so the light curve on the top is actually a dip that Kepler saw of the Boyajian star. I
Yeah.
forget which one it is. It's 1500. Yeah, and so you could
Right.
see this. I think they call this one like the Batman dip. Uh,
Point. Oh yeah, sure. Okay.
yeah, and you could see that this was a tiny, tiny little dip, right? About
Yes.
like
Uh-huh.
less than 1% or so,
Uh-huh.
um,
Plus.
on
Yes.
the time scale of about 20 days.
Okay.
And then on the bottom, we have one of our newly discovered systems
Okay.
of a 25% dip,
Oh.
right? But
Uh-huh.
on the time scale of 1,000 days.
Wow.
And what is really fascinating, right, is that
Right.
there's a lot of similarity in the structure. And of course, we're not making the argument that this is the same process, right? But really, just to give you an
Right.
idea, right, like the shapes kind of look similar. So perhaps really we're getting to probe here maybe what we saw for the Boyajian star, but on a completely larger scale, right? So it could be more dust, a bigger object, whatever that thing is. But this just gives you an idea of scale comparisons between Kepler and ZTF, for example.
Yeah, very good. You got it in two bands, two RNG. So yeah.
Yeah. So that's a curious one.
Yeah, I like this one.
Um,
No green here.
no green there, yeah.
Right. In fact, no green there, no green here. Interesting. Okay.
Yeah. So that could be in part due to the ZTF cadence. Maybe there's a couple bad nights, or maybe they swapped out the filter or something. But we got lucky in the sense that we captured that core of that dip to detect the system.
Very cool. Good.
So in the other sections we kind of start to think a little bit more. Okay, now, so what kind of stories can we tell about these stars? Like what are the sort of properties? One thing that we saw in Figure 9
Okay.
is we tried to measure the shapes of the dips. So we measure basically something called the symmetry score.
Yeah, let's cover that fine.
Yeah, so the symmetry score is pretty simple in the sense that we're essentially measuring the integral of the dip, and we're
Hmm.
just basically comparing it between the left side and the right side with
Yes.
respect to the midpoint of it. So essentially, if you have something that's skewed on one side or the other, it would basically tell you like how skewed that light curve is. So you might have something that has like a really sharp ingress and then takes a really long time to come back to its quiescent, and then the other way around, right? That's an interesting property that could tell us something about
So a
the
low symmetry score means,
symmetric.
thank you.
Yep. So zero would basically
Right.
be
Right.
a
Numerator goes to zero.
symmetric
Okay.
bell curve. Yeah.
I'm with you. Okay.
So
Sounds
so we
good.
measure this for the light curves,
Mhm.
and we could see that it seems for the most part, most of them are hanging around zero, but
Okay.
it appears that there's a tiny little bit of skewness
A little bit.
towards negative one, the
Yes.
negatively skewed. Yes.
Yes.
So we believe that these are what we think as
Okay.
fast ingress and long egress.
Okay.
So you can imagine really, really steep drop off, and then takes a really long time
Let's
to
climb
rise.
out. Right.
And perhaps that is a foreshadowing to what we're seeing. Maybe we're seeing dusty structures. So if you have like a dusty blob that is orbiting your star, which perhaps is originating from planet formation, for example, right? These
Mhm.
structures are not going to be symmetric, right? So they might have really long tails. So
Right. Right. Right.
perhaps this
Mhm.
is a hint towards that. Perhaps, it wasn't really the smoking gun evidence, but we definitely noted in the paper that this could be something that we're seeing.
Very cool.
So there's some curious things about that.
Hmm.
Um, Other
Hmm.
curious things is then we go about measuring the colors of the dips. So
Okay.
if we look at, let's see, maybe let's do figure 10.
P10.
Yeah. So
Uh,
lots of color figures here, but yeah, we'll
color.
stick with 10.
Okay.
So this one is essentially measuring the difference in color between the quiescence, which is G minus R a naught,
Oh, yeah.
minus the G minus R in the dip. So
Okay.
basically, is there any color difference, right? So if it's dust, for example, right? If it's like micron size dust, we would expect maybe like typical ISM like a reddening,
Yes.
maybe. If it's other kinds of dust or it has more complicated properties, perhaps it would make things look a little bit more bizarre. So basically, what we see is that it's normally distributed maybe around zero-ish, meaning
Hmm.
that a lot of these eclipses are actually gray, which is interesting.
Yes.
Some of them are very red, so those are on the negative side. So
Yes.
it seems like most of them, a lot of them are like on the red side, and then the ones that are to the right of zero are getting bluer. So
Mm.
maybe we're getting some scattering effects in there, like forward scattering,
Yes.
if we're
Right.
dealing with large dust columns here.
Uh-huh.
Um,
Uh,
so again, it's hard to tell with just two bands, of course. So, we're not attempting to understand what is the grain size distribution and like what kind of dust it is.
right. Right.
Unfortunately,
Right.
that would
Right.
be
Right.
really difficult to do with two bands. But we're
Right.
noting that like there is a spread in the color, right?
Yeah.
Not all of them are red, because if you expect it to just be ISM like dust, then all of this should have just been to like skewed to the left.
Yes. Correct. Yes. Uh-huh.
Yeah. Yeah.
Oh,
Mhm.
I smell a future project here. Okay.
Oh, okay. Yeah, I would love to hear it. Some other curious things. If you look at figure 13, we
13.
we see actually a statistically an
Okay.
interesting correlation between the time scale and the slope of the G minus R colors.
Okay.
So essentially, what this is telling us is that things that are taking a longer time to do their eclipse or their transit
Hmm.
um, have higher color dependence.
Yes.
And
There's evolution.
yeah, there seems to be some evolution there. This might also be a bias because things that are taking a really long time also will have the best color sampling, right? So you can
Yeah.
imagine, right? Like
Ding,
if
ding, ding,
something's
ding.
taking like 6 months to do a dip, right? We're going to have 6 months of data versus something that might have like, a couple of days.
Right.
So this could simply just be a selection effect, but still, it would be potentially interesting to investigate that more in depth. But
Yeah.
that was something that we weren't really expecting from the color
Hmm.
evolution.
Yes. Okay.
So
Mysteries
that's
continue.
colors. Yeah. So there's a lot of mysteries about the colors. Unfortunately, two bands won't tell us a lot, but we just noted some interesting properties.
It can point in some direction, yes.
Yes, yes. So then we can go to section 4.4, where
Demographics.
we talk about demographics. So now we start to think about this. Okay, so we play this hypothetical game. Like, what if all these stars are the same kind? Maybe we're seeing the same, you know,
Oh,
physical process,
oh,
perhaps.
yeah. Okay. So let's keep
And
it.
so let's
Yeah.
consider them as a demographic. So
Okay.
what are their shared properties? So we could see, for example, that a lot of them on figure 14 fall very tightly in the color magnitude locus that you could see.
14.
So
Oh,
that's a relief to us.
indeed.
Okay, good. We did a good job in our selection function. So,
Ah, yes. Here we go.
so
Yes. There's
we
our
didn't.
banana. There's the banana.
There's our banana. So we're able to recover a banana, which is
Good.
good news. Okay. You can see the temperature distribution of the stars up there. Uh, so one thing is, like, for example, you might notice that there's a peak at 6,000 degrees Kelvin. We don't think that this is real. We think this is most like the selection effect
Mm.
from Gaia,
Hmm.
because I think that's essentially a manifestation of the Malmquist bias. So essentially, we're
Right.
biased towards the brighter stars.
Right.
Essentially,
Right.
yeah,
Right.
yeah, yeah.
Mm-hmm.
And in this section, we kind of look for sort of any if these stars are part of any like open clusters, or if
Yeah.
they're part of any star forming regions that we could obviously tell. And we don't really see any systems. Well, I should say there's maybe like one or two in there that could perhaps be in some star forming regions, but for the vast majority of them, they don't seem to be part of any star forming region that has been cataloged
How
at
about
these
how
distances.
about unresolved binaries?
Yeah, binaries. We'll talk about binaries
Okay.
actually in
Okay.
a bit when we start to
Okay.
think a little bit more about the specifics of interpretations of what these systems could be.
Okay.
Yeah. So yeah, if you look at figure 16,
Okay.
uh,
Ooh, nice.
this is
Okay.
the
Where
position
are
of
they?
all. They're kind of scattered all across, right?
Yeah.
Most of them seem to be in the disk, which
Sure.
checks out, right? That's where most of the stars in the Milky Way hang out.
Yeah. Yeah. It would be weird if
um,
you had them all up here down there. Yeah.
yeah, yeah. But I think what
Okay.
this figure is demonstrating, right, is that the positions of them don't necessarily correlate with like high extinction regions or regions where there's like a lot of star formation, right?
Right. Right.
So this is not saying that, like, maybe they're in some star forming regions that we are too far away,
Yeah.
right? That could be one scenario. But in previous studies, people have noted that, oh, it'd be interesting to look at the sky distribution. And so we don't really find anything special in the sky distribution is kind of the point here. They're kind of scattered all across.
Yep. Cool.
Um,
Okay. Right.
Yeah, and then the other thing that we try to talk about is the age. Of course,
Ooh,
aging stars is a very
hard
difficult endeavor.
game.
Of course,
But
and
we
that was
give it a
not the
whirl. We give it a whirl.
we give it a try because we're
Right.
astronomers.
Right.
And
Okay.
so here in figure 17, we essentially look at the absolute galactic scale height. So the scale height of the positions of these stars.
Okay.
And our data is in black and in the reddish sort of dashed line. So we use both the distances from Baylor-Jones and the Gaia parallaxes. So
Uh-huh.
kind of just double metric on the distance. And then we compare that basically to the low alpha and high alpha disk.
Yeah.
Um,
Okay.
and again, this is not, we're not going to come out here and say, well, we've discovered X number of age of stars. But what we do see is that based off this distribution, it seems like it's mostly consistent-ish with the low alpha disk.
Closer to the gold line, yes.
Yep.
Correct.
So perhaps pointing to the fact that these are predominantly young stars,
Okay.
young-ish in the galactic sense.
Okay.
And so, perhaps this is the first step in the direction of, okay, well, what's the age of these? And I think, the age is something that's truly really interesting to think more about these systems, because the age will tell us a lot about the context of the material
Correct.
that's transiting, right? So
Right.
if it's a really young star, maybe it's forming planets. If it's more mature, maybe it's engulfing its planets, for example.
Hmm.
That could be one.
Cool. Good.
Okay, yes,
Picking.
yeah. So let's see. Then we play the game of sort of the sanity checks.
Good.
So the first thing that we address is the periodicity. Is there any periodic structure to these Dipper stars?
Yeah, okay.
Conclusion is no. We looked through periodic catalogs
Okay.
from ZTF.
Okay.
We ran our own Lomscarlo periodograms, and we didn't find anything.
Okay.
This makes sense because systems that have one dip, right, will only have one dip. So we didn't see any structure in there. But even besides the high amplitude dips, we didn't really find any sort of significant variability, periodicity that was coming from these. And systems that had like 2 or 3 dips, it didn't seem like any of them were obvious to us that they're periodic.
Okay.
So as far as we could tell, most of them are stochastic. Of course, this is only using 6 years of ZTF photometry. So perhaps if we had a longer baseline, this could be done again, and maybe we could find other dips.
Okay.
But in the time frame of ZTF, we don't. None of these have ever repeated before,
Okay.
or do not seem to be periodic.
Aperiodic.
Aperiodic. Yep, aperiodic. Truly aperiodic.
Okay.
The next thing we do is what about the infrared properties? Now this one's really interesting. So if you go to figure 18, we asked the question, well, okay,
Yes.
what if all of these stars are some subclass of like some young stellar object and they're under disguise?
Why is it?
Okay, so we looked at 2MASS and WISE.
Okay.
And so here you're looking at a color diagram,
Mm-hmm.
and the circular points with the color are our sample. So it was about 66% of our sample that we could find.
Mm-hmm.
And what we see is that if they fall pretty much on a tight locus, that's basically the main sequence. And then those triangles and squares are essentially typical young stellar objects that we found from the literature. And we've broken it down here in this color space. And so the conclusion from this is that there isn't really any bizarre infrared properties. These all seem to pretty much be where we would typically expect main sequence stars to be. No clear infrared excess, no variability coming from WISE. NeoWise has been observing some of these stars for like the last 10 years or so. So we had 10 years worth of near infrared photometry. We don't see any clear dips there. Of course, there's an asterisk there, right? Because essentially, right, like NeoWise has its survey window is like, I think like several months. So it'll come back to the same part of the sky, like I think twice a year or something like that.
Okay, so yeah.
So on those time scales, we don't really see anything.
Right.
So these would be longer time scales. But if there was something that had clear infrared access, we would be able to tell. And so that color bar that you see Z of W1 is basically the deviation of the WISE-1 light curves. So we don't really see any system. Like maybe one system that has maybe a 3 sigma variability, which could potentially be interesting.
Okay.
So no infrared.
Okay, well, that's a good sanity
then
check. It's a good sanity check.
And then our last sanity check was we also looked at the IFAS. So if you go to figure 19, we looked at the another color diagram in H alpha and in the optical. And so those pink dots are all our stars that we found. This was a much smaller sample, about like 40%. The dashed black, the black lines are essentially the main sequence locus. So, where typical main sequence stars hang out.
Good.
And those squares with the colors are essentially H alpha emitters, and it increases as a log of the H alpha equivalent width. So basically, the higher up you go along this track, the more H alpha that we're seeing, right?
Yes.
And to our surprise, we did discover one system that's that top right star, which seems to be a clear H alpha emitter. So that was an interesting find. We think it's a symbiotic binary that somehow sneaked in there. And what's really interesting about some symbiotic binaries is that their timescales of how they transfer material through stellar winds takes a really long time. It could take decades in some cases. So It might be one of those rare cases that we found one that just happened to
Be
pass
in the
on a lot of
window.
material.
Right, right. Or you got lucky when it happened. Right.
Yeah. So that was the only one. So, you know, I was happy that we found like at least one outlier. I was getting a little worried there.
Good, good. Great
Yeah.
stuff.
So in conclusion, a lot of normal stuff is kind of what a lot of this discussion is trying to point to.
Right. These are not completely weirdos.
Yeah. Normal stars in the catalog sense, but weird stars in their light curves.
Jeez.
So that leads us to the discussion, which is mostly just text of going through different scenarios. For
Right,
example, we talk about eclipsing binaries.
right.
And since you asked about eclipsing binaries, maybe I could talk a little bit about that.
So let's talk about eclipse
So,
binaries.
so eclipsing binaries are sneaky, of course. And so there is high chance that some of these might be eclipsing binaries. The thing that is doesn't really add up to what we see in the light curves
Right.
is that the structure of the light curves, the dips of themselves, are not the typical sort of eclipsing binary eclipse, which should be mostly a uniform transit, right?
Right.
Um, so there's that argument. Then there's the other argument of timescales, right? If you wanted to get an eclipsing binary to last for like an eclipse to last for like 100 days, right? That would mean that you need to be really far out, right?
Yes.
And so your probability of detecting that, shrinks by a lot, right? It
Yes.
goes
Yes.
as one over the semi-major axis.
Yeah.
And so the further out you go, you would also anticipate that Gaia would see them, right? Because Gaia has really high astrometry. And so we would imagine that if these are freaky coincidences of eclipsing binaries on, humongous orbits,
You
then
would have seen it.
perhaps
You would have seen it.
you would have assumed that Gaia could see them.
Right.
But also that doesn't also add up to the sense that the transit depths and shapes themselves are also just not consistent with an eclipsing binary picture.
Okay.
So if you remember from that table that we had, like the 20 symmetric systems, perhaps those could be. Maybe that's a legitimate argument for those. So maybe that would need to be more. We need to do more investigation there. But for the rest that are irregular and asymmetric, we just simply don't see an eclipsing binary story in that case.
Okay. Thank you.
We do the same thing for cataclysmic variables. CVs are interesting as well. Star spots. We pretty much tried to think of anything that can cause a star to dip in brightness, as far as we can think
stellar
about.
material in intervening ISM. Yes.
Yeah. So ISM, we consider like what if it's a blob of ISM material? Probably not. So that leads us to the last two sections, which are talking about, let's see, let's do figure 20.
Maybe 20.
So
Right.
the last two scenarios we consider are disks, so debris disks around main sequence stars, and circumstellar or circumplanetary disks.
Okay.
So what we did here is we essentially, for the majority of our stars, we didn't find any W3 or W4 fluxes from WISE. So this is somewhere in the 10 microns, I think 10 microns or so regime, or somewhere around there. And so we basically found a bunch of upper limits.
Okay.
So what these upper limits are telling us, right, is that if we were to see a star that has like a debris disk around it, what would be the expected W3 and W4 magnitude that we would observe? And so we essentially take a toy model of a disk, and what we see is that in order to reproduce all these upper limits at different distances that we're observing them, you would need to have really cold and diffuse disks. Right, so somewhere in the like 300, 400 Kelvin regime. So right around where you typically expect debris disk. So essentially, what we're saying is that if these are very plausibly might have debris disks that could be driving some of this variability. That's like a scenario that we need to account for.
Definitely.
So we raised that possibility, right? Because if there were hotter disks, right? If there were younger disks and they're a little bit warmer, then we would expect there to be some moderate excess in the W3 and W4 bands.
Yes, I'm with you. Cool.
Yeah. So the sort of last two sections is building up a case that the material that we're seeing is most likely circumstellar. So perhaps originating from planet formation. So perhaps planets are interacting, um,
Mhm.
and they are perhaps on really wide orbits. So,
Okay.
right, so they're taking a really long time. So that takes us to figure 22, right?
Sorry, I
Which
didn't
is
mean to push you. I was just
essentially,
looking.
oh, no, 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 the figure 22 is perfect. It kind of makes a perfect case that because these time scales are taking really long time, we
Okay.
could use basically an assumption that the transverse velocities are proportional to the ingress of the dip. So basically, if you have some material that's passing from the star, the
Yes.
way that star begins to dim, that slope will tell you something about the velocity, which you can then relate to how far it is.
Okay.
So the takeaway conclusion from this is that if this material is dust, it must be really far on orbits that could be like 10 AU or 20 AU.
Yeah. Right.
And these are, of course, upper limits. So, of course, they could be closer. But if it was closer, then you would see the transits happening more frequently, right?
Okay. So this is
You
for
know?
solar mass, and this is for a point 0.8 solar mass.
Yeah. So we kind
Okay.
of cut
I'm
our
with you.
sample kind
Yeah,
of
I'm with
in
you.
that way. Hmm.
Uh-huh.
So we kind of leave it at that. Perhaps these could be circumstellar material, so dust clouds, or it could also very legitimately be disks, like circumstellar or
Binary.
planetary
Planetary.
disks.
Yeah, yeah.
Yep, and you can distinguish between the two with the archival photometry that we have in hand.
Nice.
And so yeah, that's kind of that leads us to the conclusion. Maybe before we go to the conclusion, I just wanted to point out that there's three appendices.
Yes, sir.
Um, yeah, so Appendix A has all the Dipper light curves. So perhaps we could show here just a
Yeah,
few, so
let's
you can get
look
an
at it. Let's look
idea
at
of some of them. Yeah,
it.
so these are just the single dips, and you could see a lot of them have really small dips, and we kind of highlight where our scoring algorithm finds the dips.
Yep. Yep. Gray
Um,
bands. Yes.
And there's some like even more extreme cases. There's stuff that are like on really long time scales on top of the dips that we find, right? A lot of complexity to these light curves,
Yeah.
which we're still untangling.
Yeah. It's a
Um,
fantastic data set. So,
yeah, it's a beautiful data set.
right. To do this kind of investigation. So,
Uh-huh.
very cool.
Yeah, and then
Uh,
Appendix 2 essentially has, the coordinates for all these stars and the our
what-
selection. Yeah, if you go to I think it's table 2. Yeah,
table
table
two.
2 has. Yeah,
Oh,
so
yeah.
if you are a curious researcher and want to investigate what one of these stars is, by all means, here you go. This is this is the list. Please help us figure out what these are.
Absolutely. And I want to point out this is not the full table, right?
Yes, not the
In
full
its
table. Yes.
entirety is not full table. So the full table is available online, so you can check it out.
Yes, absolutely.
Clean readable too.
And then, yeah, in Appendix C, essentially,
Okay.
we
Okay.
looked through all 81 systems through Simbad and Vizier,
Yeah.
and
Yeah.
we
Uh-huh.
we kind of make some comments about like, oh,
Oh,
one
cool.
star has flagged as a YSO, but has like a
Huh.
probability of zero,
Yeah.
because I think that should be noted that some of these
Yeah.
stars have been in previous catalogs.
Mhm.
There's some interesting flags to it, so uh, do whatever would you like with this figure, but this is kind of like again our due diligence of what we found through the data archives.
Yeah, you want to do a complete or as complete as investigation as you can. So,
Yes,
yeah.
yeah, absolutely,
Laser
yeah,
or Wilson. Okay, very good.
yeah, and so that leads us to the conclusion of the paper.
Mm,
So yeah, this is
I'll get there. There we go.
the largest systematic search for main sequence stars.
Hmm.
We find analogs to the Pleiadian star, what we believe. Um, let's see. We investigate the timescales of these events. We talk about like what are the averages that we see and
Yes.
the extremities of the timescales. We talk about how normal um, the auxiliary survey data that we find from like infrared and H alpha seem to be, and we argue basically that these are what we think as main sequence stars.
Yes.
Um, and we can't distinguish between circumstellar material and perhaps disk eclipses. So that's still a mystery that needs to be solved. And so we need more data and more opportunities to essentially investigate a lot of these systems.
Very cool. Very cool. Andy, beautiful work. Beautiful work.
Thank you so much.
You're welcome. Thank you for that. And thank you so much again for walking us through your very lovely hunt for dippers. Very cool. Let's see. You kind of mentioned it, or you brought up several points,
Mhm.
actually, on where this might go from here. So, sort of, since there's so many possibilities, maybe I should focus on the nearest. What are the best shots to take close by, let's say, over the next couple of years? How can we improve this situation, either on determining what is causing the dips, more characteristics of the dips, or if there's any chance of increasing the sample size from 81 to, let's say, 810. So
Yeah.
where do we go from here?
Yeah, I think two things come to mind. I think one thing is to think a little bit more carefully about the sort of observed characteristics of, let's say, dusty occultations from the modeling side. So
Okay.
perhaps if we had some dust that's really far away from its host star, what are its radiative processes and properties that we would typically expect from a ground-based survey? That work, for example, I think could really set the ground of where do we go from here. So that's one thing that would be interesting. The other thing, I think a lot of this work is more of a call to the community that a
Yeah.
lot of these transits, these very puzzling events, have happened already. And so in a lot of these cases, we've lost our opportunity to sort of understand what it is.
Hmm.
And that's nature maybe perhaps teasing us a little bit, like, hey, there's something weird going on there. But but perhaps this is a wake-up call to the community that, well, we need to start going after these in real time. We need to pay
Okay.
attention to
Okay.
the alerts that are coming from different telescopes. So, for example, the Vera Rubin Observatory, which is coming
For
online
example,
very
yes.
soon,
Right.
and
Right.
many other amazing observatories that are producing millions of alerts each night. This is a fantastic opportunity for us as a community to focus on stars and think about things that are disappearing.
Yes.
Right?
Twinkle, twinkle, twinkle,
And
twinkle.
and allocate the proper resources to
Yeah.
understand these. So
Right.
do spectroscopy, do the deep infrared photometry, do the follow-up that
Right.
they deserve. And I think that will tell us a lot more. So I think it's clear that they happen, and I think that now we can move into a regime where we could start to discover them in real time, so we
And
can get more data
characterize them.
and characterize them. Exactly.
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 Very nice.
Yeah.
Beautiful. 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 Well, it's going
Yeah.
to be really exciting over the next couple of years to see this
Absolutely.
nascent field. Um,
Yeah.
so very nice.
Yeah. Yeah.
Cool. All right, Andy, thank you so much once again for walking us through your very lovely article.
Amazing. Thank you so much for having me.
Yeah, and that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Dip, dip. Bye bye.